我刚刚没看到。
县市的不一定会来，他们今天应该会先把是打我。
压车的，他有压车吗？
他才没有回家。
拜托那个压车的，对，请那个请那个外县市的一定要挂在身上，不然每次他们都去行李箱再去找，那我们8点就搞到很晚，他们才能上车。好，你们3个人压车，那就3辆车。
OK。
你没有压车吗？
还有固定的停车。没有出来。
为什么他们早先上？他们厕所。是这样吗？
大概会积累很久。 那个要不要关掉？对啊，有点亮。
好，这个会场是不能吃东西和喝饮料的。如果你需要饮食的话，请到那个会场外面，谢谢。
下午义务可以参加吗？会不会留下？会啊。那你们还有2个呢？去买早。都还没有过来。3个题目你们有没有准备啊？他那个 好，那你赶快听一下。他们看一下，学习。网络可以吗？
可以。
对啊，我就知道。性别歧视。
这个灯是。录影是 OK， 但是看起来是偏黄。
Okay. Good morning, ladies and gentlemen. It's a great pleasure that the 4 days tournament finally comes to the end, and we have 3 very outstanding groups join in our final competition. And today's final physics fight, we follow the international games rule. So we have 11 juries, and I am the chair, and I will not join to give the points. I will focus on making all the things go smoothly. And this morning's event, I would like to start from introducing all the jury members and all three teams to everybody. And since we have the internet broadcasting at the same time, so please all members when you introduce yourself, please stand up and take a look at the camera lens. Okay, I would like to start from Professor Jia. Please introduce yourself. Microphone is there.
Good morning, Chairman Professor Xu, and I'm Professor Chia from National Taiwan Normal University. I'm very happy that we have outstanding teams, and also we have very outstanding students come to the TYPT. And I'm honored to be the juror of the finals. Thank you very much. Thank you.
Good morning, everybody. My name is Fang Yulo from Taiwan Normal University, and it's a pleasure to be here as a juror. And I would like to. So I think everybody will have a very good performance during the tournament and this morning. So thank you.
Morning and everyone. My name is Hong Yiquan. I'm from National Taiwan Normal University. Thank you.
I'm Dai Nifeng, come from Taiwan University.
Good morning, everyone. I am Zheng Wenzhe, from Danjiang Daxue.
Good morning, everyone. I am Hong Weiqing, come from Military Academy. Thank you.
Hello, everyone. My name is Jia Hui Yang. I'm from Fengjia University. I'm very happy to be a part of this game, and I hope to see all your out of the best performance, and we are going to have fun. Thank you very, very much.
Hello everybody, I'm Welcome Steve Xu from National Taiwan University. Thank you.
Good morning, I'm Ming Jin Shi from National Zhongqing University. Thank you.
Good morning, my name is Fu Zuyi, come from National Taiwan Normal University. Hope we will have a nice time this morning. Thank you.
Good morning, Chen Guo. I'm from National Zhongzhe University. Thank you.
Okay, thanks all the jurors, and I think I have to introduce myself. My name is Yongyuan Xu. I'm the this year's project manager, so I as following the tradition, I am the chairman of this final physics fight. And following, I would like three teams to introduce yourself. I think start from the reporter.
Okay, so hello everyone. I'm the team captain of Xiaomin, and I think this is my teammate Xie Weizhen, and that is Paul, and that is Weizhen, and that is Yulong. And we'll make our best to make a great performance in this debate. Yeah, thank you.
Next, the opponent, please.
Okay, good morning everyone. It's a very great honor to be on this stage, and I would like to introduce myself and my teammates. My name is Jason, and this is Ruth and And that's Fred. Over here is Kevin, and he's Bobby. Thank you.
The reviewer, please.
Good morning. We're a team in Pioneer, and I'm the Captain Harry. This is Danny, Alton, Jasmine, and Jonathan. Thank you.
Thanks all three teams. So this morning's game that the question already been chosen last night. So we will skip the first two stages of the schedule. So we will start from the preparation of the reporter. That would be 5 minutes. So we start now. And the problem of this stage is the problem they chose is number 11, contactless caliper. Then now we start the preparation time. During the preparation, I would like three teams to write down the presenter's name on the paper, on the board. Okay, time's up. So, reporter, please take the floor. You have 12 minutes for your presentation.
Okay, hello everyone, I'm today's reporter and I will talk about problem number 11, Untitled Chapter. So first, we take a look at the problem statement. The problem statement asks us to invent and construct an orbital device that can use this laser to measure the properties of a glass sheet continuously, such as refractive index and thickness. And actually, we will use as less contact with glass sheet as possible. And actually, still need some in my experience, still need something to hold the glass sheet in my experience. And let's take a look at a short simple outline. And we will report it by two parts. And it's model one. Model one is the geometric optics, and model two is wave optics. And first, this is the theory. And if we shoot a laser on the glass, and we use the refraction and refraction, and we can get a displacement. And if we use two incident angle, and we can get the two displacement, and we can solve the equation, and we can get the refractive index and thickness. And this is our setup. And this is how we work. And we shall first determine the incident angle continuously, and finding the maximum brightness by adjusting the incident angle. And the brightness angle will be defined as perpendicular incident angle, just as this picture. And this is the method. And set up a screen to detect the two light dots produced by the light beam, and changing the incident angle theta I by turning the turntable. And this is the method. And we will solve this equation, and the t is just like this, and the n is just like this. And actually, we will compare with the experience by measuring the real thickness and refractive index. And we will measure the real thickness by lower vernier. And we also measure the real refractive index by shoot the laser on the glass directly. And this is how we work. And we use a projector and use pencil and draw on it, and according to the Snell's law, and we can get the real refractive index. And this is the experience result. And this is the displacement light beam versus the incidence angle. And this is for 2 millimeter. And the error percentage is about 12.1. And this is for 2.75. And the error percentage is about 3.8. And this is for, and the error percentage is about 3.1. And this is for 4.75 millimeter, and the error percentage is about 2.5. And the refractive index is about 2, error percentage is about 2.1. And that's the conversion. And this is the error, experience error between this. And this is thickness, this is thickness error, and this is refractive index error. And we will talk about the model 2, wave optics. And first, when the refractivity of parallel polarized light is 0, which means the incident angle is Brewster angle, just like the picture. Yes. And just when the Brewster angle. the refracted light is vertical to the refracted light. So according to the Snell's law, we can get this formula, and we can use the formula to calculate the refractive index. And if we put a glass and cover one of slate, and we can get this formula. And first we measure the refractive index in the Brewster angle and put the refractive index into the formula, and we can get the refractive index and then get the thickness. And this is the experience setup. And this is the gas sheet we will measure. So let me show how it works, just like this. And just when we shoot a laser into the glass sheet, and just when it is Brewster angle, and we can rotate the polarizer, and when it is Brewster angle, and the polarizer will block all the refracted light. And this is the Brewster angle we measure. And this is the refractive index we measure. And this is the data result. We measure four different types and thickness glass sheet, and the general data is the refractive index. The general refractive index of glass sheets is about 1.55, and we see the data result with the real value. And this is the double slit interference setup. Okay. And this is how it works. And N is the refractive index we measured in the previous experiment, is Brewster angle experiment. And put the refractive index we measure into the formula, and we can get the thickness of the glass sheet. And this is the error percentage of measuring. Okay, and let's look at the discussion. And first, in the model one is a geometric optics. Okay. And the process is, this is actually a contact. And when the thickness is big and the displacement is more accurate. And there are some constants when the thickness is small and it may not available. And the model 2 is wave optics. And when the thickness is small, the properties can still be measured. And the constant is when the thickness is big, the area of optic path difference gets bigger. So this has more contact. And in experience, it has more contact just because we put a double slit on it, so it gets more contact. And this is the comparison. As you can see, the model 1 is suitable for big thickness, just like this. And model 2 is suitable for small thickness. And then we will talk about the absorption coefficient. And this is our setup. Yes. And first, so we can define that from this picture. We can define that the intensity of transmittance. The transmittance is ST. So we can get this formula. And the formula is based on when the incident angle is 0. And we can use the formula to calculate the absorption coefficient. And when the incident angle is small, which means the refractivity is small. And refractive is small, which means the intensity of transmitted light is bigger. And the way how we get transmitted light intensity is rotating the rotating disk and use light sensor to collect the data finding the highest intensity. And just like this. And the transmitted intensity when incident angle is 0, just like the video. So how to get the refractivity of gas when incident angle is 0? From Fresnel equation, we get the formula to calculate the refractivity of gas sheets when the incident angle is 0, just like this. And we put the data from previous experiment into the Fresnel equation, and we can get alpha. Alpha is absorption coefficient we will measure. And this is the result. And this is the absorption coefficient we measure. And this is the data result. And result is from 0.006 to 0.0011. And the real value is about 0.01. And the end is the conclusion. We propose two methods to get the properties. And model 1 geometric optics suitable for big thickness. And the model 2 fixed optics suitable for small thickness. And by error analysis, we can know the variability of this method. And our properties, we measure absorption coefficient. And this is my reference. And thank you for listening.
Okay, thank you. So now the next stage is a question from the opponent.
Good morning. Several questions I want to ask first. So, in your experiment, you used the same red laser to measure all your refractive index, thickness, and absorption?
In the double slit interference, we use high-end laser because it is more.
So in the other experiments, you used red laser.
Yes.
Okay. And you said there are two. You had two experiments suitable for different thickness, right?
Yes.
Do you have a limit where under this thickness is suitable for experiment 2 and above is suitable for experiment 1?
Not really.
Not really?
Yes.
Okay. And the way you measure, in experiment 1, you have to measure the distance of the two dots, is that right?
Yes.
And how did you measure it? You said you had a screen.
Yes. And we use a vernier to measure it.
Use what?
Vernier. Vernier.
Vernier. Oh, okay.
It's a vernier.
And that's all my questions. Thank you.
Thank you.
Okay, now we'll proceed on the preparation of the opponent. Reporter, you can take a seat. The time will be 3 minutes. The next stage would be the opponent takes the floor. You have up to 4 minutes to take the floor, and any remaining time will be added to the following discussion time, and total time will be 40 minutes. Please.
Good morning, ladies and gentlemen. After seeing the reporter's report, we were in awe how well they did at their experiments. And we think that their experiments are very detailed, and we applaud them. And of course, we found that they use the same template of TPPT as we do. So we think that shows their level. Okay. But however, there are still some questions we would like to clarify in their experiments. So first, in their theory, they said they had 2 experiments, one suitable for larger thickness and one suitable for lower thicknesses. And we're curious that if we give them one piece of glass, what is the limit of the length that if they will choose experiment 1 or experiment 2. And of course, we all know that the color of the light affects the refractive index. And we're curious why they only use a red laser dot. And if they maybe use a green laser dot, would the refractive index change? And in their experiment, they used the screen to detect the length between the light dots. And we're curious how accurate it is. Because today's topic is telling us to invent a device to measure refractive index, thickness, and absorption. So for a measuring device, the error is very important, and we want to know the accuracy, because this is the heart of this question. And so we're curious that in some graphs they had a if I didn't remember wrong, they have a 12% error, and we're curious where it came from, and we wish to discuss with the reporter how to lower the error and make the experiment better. And we're curious that because they did their experiment, how many times they did their experiment, so how accurate they can improve to be. And in their conclusion, and in their last experiment, for the other properties, they measured the absorption of a glass sheet. And we're curious also because they use a red laser dot to see the absorption. So if the glass sheet has color, maybe it's a green glass sheet or a red glass sheet, would it affect the results? So can we move on to the next stage?
Okay, now we move on to the discussions. So, reporter, please.
Okay, so you said you used a red laser beam. So would the color of the laser affect the result you got?
I think the red laser is more easy to.
Why not use a green one?
Just the highlight laser we use is red.
But you said you only use. But you said in experiment 1, and mostly in experiment 2, you use a regular red laser beam, right? Is it kind of like this one? The one you used to do your experiment 1 and 2. Use a red laser beam.
What? I said green.
We
said in the double slit interference. We just use highlight laser.
Okay, in the other experiment, in the experiment 1 and in the Brewster's angle experiment, you use a regular red laser beam, right?
Green.
But you said, okay, green laser beam then?
Yes.
Would the color of the laser beam affect the result you got? Yes or no?
I think no.
No. So the reporter here is saying the color of the laser beam wouldn't affect the refractive index. Right?
I think maybe a same difference, but I think it's not very big.
So you don't think the changing of the color of the laser beam affects significantly to your refractive index?
Yes.
Okay, then let's move on. So you have 2 experiments. What are the limits between them?
Actually, each glass sheet has different refractive index. So in my experience, I think that the limits not all the same. So I think
about where? you said in experiment 1 it's more suitable for thicker glass sheets, right?
So you think, so you said that the limit is just for the glass sheet? But there are many material we can measure, but today we just measure the glass sheets. So the limit you see?
In your conclusion, you said that the experiment 1 is more suitable for thicker glass sheets.
Yes.
So below what limit will experiment 1 lose its accuracy?
When the thickness is small, yes.
When what?
When the thickness is small, the accuracy is lower, yes.
Yeah, below where? Below where? And why does it lose its accuracy?
Because the laser dot is very close to each other. So because the dot projected to the screen is very big, and if the laser dot bigger than the distance between the two dots, and I think the error is very big.
So you mean to say when you have two laser dots and when they contact, your experiment will lose its accuracy, right?
Yes.
Okay. So you said you used a device to measure the distance
and just
of the two laser dots, right?
Can you say that again?
You said you used a screen to measure the distance between the two laser dots.
Yes.
How accurate is it?
Accurate?
Yes, how accurate is it?
We use a vernier, so I think it's 0.05 millimeter.
0.05 millimeters.
Yes.
So then, from this data, you can get how accurate is the thickness. How accurate is the result of the thickness of the glass sheet? You're not sure. Okay. Can I see your experiment 1? So in your experiment 1, you had to use two different angles to solve two equations to get the N and the thickness, right?
Yes.
Is there any possibility for you to use only one angle to get these two results?
I think not.
You think not? Because we think that your experiment is pretty well, but it's still a tiny bit complicated to use. So maybe there's a way to improve this. So we have glass sheet here, right?
Yes.
So when the light shines through, it will one laser beam will reflect.
Yes.
And one will refract, reflect, and refract, right?
Yes.
And because you know the position and the angle of this glass sheet, maybe you can calculate if there's no glass sheet but just a mirror here. There is what the laser beam will go like this. And maybe your screen is here. So if you measure the points between these 3 points, is it possible for you to get these two data with just one angle? Because the distance between these two beams are affected by the thickness. And after you get the thickness, you can put it into this equation and get the N.
You first put the thickness into the equation. The thickness you put is the real thickness.
You can declare the thickness by the distance between these 2 points. Okay, let's move on to the next question. And in one experiment, you have a 12% error, right? One experiment.
Which experiment?
I think page 40. I'm sorry. Page 37. Sorry. 30. We can see there that one error bar is significantly larger than the others. Why is that?
Can you say that again?
These two bars are significantly larger than the others. Why is these two error bars larger?
I said that the double slit interference is more suitable for the thickness is small.
So why? So according to your experiment, where does the error come from?
I think if we shoot a laser into the double slit influence, if the glass sheet is more bigger, which means the more light will be absorbed. So in the screen, we can get a not clear strip in the screen. So I think that's why the error is.
So it's because your light isn't clear enough?
Actually, yes.
So maybe if you increase the strength of your laser, would it be better? Clearer?
Clear?
Yeah, well, if you increase the strength of your laser beam, would the strip be clearer and thus improve your accuracy?
I think that's not paper, because if the strength of laser, okay, and then
They will, right? So maybe this way they can improve their experiment and get more accurate results, right?
That's maybe we can improve in the future.
Yeah. And your experiment 1, you used a screen to detect 2 laser beams, right?
Yes.
If we have 2 laser beams, which is 2 circles, from which point to which point did you measure the distance? Because the laser beam is a circle, not a single dot.
Yes.
So how do you measure the length?
I think in the middle one.
In the middle.
Yes.
How is your laser dot a perfect circle?
It's very close to a circle.
Very close.
Yes.
But it's not a perfect circle.
I think that's not make a very difference. Yes.
Because if it's not a perfect circle, how do you know where its middle is? If you don't know where its middle is accurately, would it affect your results?
I think that's considered error.
Okay. And so maybe to improve, maybe you could make your laser dot thinner. Or because we know that
you mean use a polarizer?
I mean thinner.
Thinner.
A smaller laser dot.
Oh.
And of course, we know that the laser matches Gauss distribution, right? So maybe you could use Gauss fitting to know exactly where the middle part of the
I think we can just use a light sensor to measure the highest density and measure the two distance.
Okay, talking about light sensor, in page 48. There is this graph where you used a light detector and got a result. You found a peak. I think it's in the Brewster's angle experiment.
No.
You had an animation about how you did your experiment.
You say this?
Yes.
This is how we get the transmitted intensity when the incident angle is 0.
Transmitted intensity when the incident angle is 0. Okay, can you play this video?
Okay.
Okay, because we saw that in their experiment, their line is sort of shaky, and we're unsure how they got the peak point. Because look, in this part, it's very shaky. So how do you know that it's this point you want to get? Or is it the inaccuracy of your device?
We believe that it is the highest intensity, so we use this intensity. Yes.
So why is it? Okay. Sorry. Next question. And the other properties you used absorption, right? Would the color of the glass affect the absorption? The color of the glass. What? Yes or no? Because we're running out of time. Yes or no?
I think yes.
But you didn't consider it.
Yes.
Okay.
But we use the same laser. So
sorry,
I think
thank you.
The time is up. So the next is that the opponent, you have 1 minute to summarize the discussion.
Okay, so after our discussion, the opponent tried to improve the reporter's device because we think it's great, but we want to make it better. So we thought of a simpler way maybe to make their device easier to use. And we thought of some ways like using Gaussian distribution to lower the errors of the distance between two laser dots, and maybe using a smaller laser dot. But there are some points which we are still curious about, because the reporter said the color of the laser beam wouldn't affect the refractive index that they got, but we believe that the color will affect the results. Yes, and so after our discussion, we tried to improve their device, and we believe that we did succeed to improve their device and to make their experiments better. Thank you.
Okay, thank you. Now we proceed on to the questions of the reviewer to the reporter and opponent, and the answers to the questions. Yeah, please.
I have a few questions for the reporter. First of all, in your first model,
Can you use the microphone?
In your first model, we can see, is your glass made of the same material?
We use different kind of gases, so we can get a different refractive index in our result.
So you changed two different parameters at the same time?
I think that just the measuring. So I think that's just the measuring.
Okay, and to the reporter, can you explain how you measured between the two dots? Because we can see that the dots are actually pretty big.
Yes.
And in your pictures, you used a ruler.
Yes, and in the discussion between the opponent and we just said we can improve the experiment by just using a light sensor to measure the highest density and measure the two density.
We can use Gaussian distribution.
Yes. I think the accuracy may more higher. Yes.
And for your model on the Brewster's angle, can you tell me which part of this you invented and constructed? Like, our problem told us that we had to invent and construct. So, did you do something to improve this?
Invent and construct, improve what?
Our problem states that we have to invent and construct a new device that helps us do this. But in your device, I saw that you used the original Brewster's angle. So, can you tell me which part you improved or?
Let me show you a video.
Okay, it's okay. It's okay.
This is how we measure the.
Okay. Okay. Thank you. And to the opponent, do you think there are any other properties that can be measured?
Other properties, yes, such as we mentioned the color of the glass is very important, or maybe they can use the position of their reflective and refractive dots to see if the glass is bent or any other properties.
Okay, thank you. And to the reporter, is your laser used by battery?
Yes.
Okay, thank you.
Okay, thank you. Now we move on to the preparation of the reviewer. You have 2 minutes for your preparation. Okay, reviewer, please take the floor. You have 4 minutes for your presentation. The clock, please. Thank you.
Good morning. I'm the reviewer of Excel Pioneer, and here is our problem on the contactless caliper. This is the outline of the reporter's presentation. First, he gave us an observation with pictures. The second, there was a theory, and he told us about geometric optics and wave optics. And the experiment, he tested the thickness and refractive index. However, I believe that since the problem told us that it had to be completely contactless, and he still had to turn the glass, so I believe that this is a part where he could improve. But he gave a good explanation on how he made the device and how he conducted the experiment. Next, we had a discussion on the error percentage, where I thought he did good at the part where he compared the results of his first model and his second model. However, there's still parts of the error that could be improved. And for the result, there is error percentage and conclusion, but however, I believe that one of his models is an original model that somebody else had already invented, when our problem told us that we had to invent and construct a new one, or at least put something new into the experiment. The first clash was when the opponent asked, is there a limit where the thickness is suitable for which model? I think that this is a really good question, because if there are two models, there should be a threshold condition where we transfer from the first model to the second model. If we get a glass, we have to decide, if we want to use the first one or the second one, which one would have the more accuracy. And the second one is, will the color of the laser affect the result? And the reporter said no. And I agree with the opponent that different colored light had different refractive index, so if we want to use different colored light, we have to use different wavelengths to calculate the refractive index of different lights to make it correct or accurate. For the second one is, the opponent said, you said you need to use a screen to measure the distance between the laser dots and how accurate is it, and the accuracy of the experiment. The reporter replied that they had an 0.05 millimeter error with their measurement, but he didn't really give us how he measured the screen, how he measured the dots between the device. And this one is, the opponent asked, why is one of the error bars so big? And the reporter said the light isn't clear enough, it's blurry. But then the opponent said that we should increase the strength of the laser beam. I disagree with the opponent on this, because increasing the intensity of the laser beam will not make it more clear. It will only make it brighter, which will illuminate the side of the dot, which makes the dot sort of bigger. It will become unclear, and if we want. And here I come to my conclusion. The problem states that we have to invent and construct an optical device that uses a laser pointer and allows contactless, meaning we cannot touch the glass, and determine a thickness, refractive index, and other properties of a glass sheet. I believe that the reporter and the opponent did a good job on several parts, but however, they did not fully discuss these couple of things. The first one was, what other properties could we test? The second one was that we had to invent and construct, and also because the reporter's laser was used by a battery, and as we use the battery, it might be unstable. So what I suggest that we should connect a laser to a DC power supply so that the laser's light will always be the same. And yeah, thank you.
Okay, thank you. We're moving on to the concluding remarks of the reporter. The time will be 2 minutes.
Oh, okay, and thanks for the opponent and reviewer, and we have a good discussion, and we also talk about many problems to improve my experiment. And first, there are points I didn't agree with the opponents. If we use the method the opponent just said, we also should use to contact the gas sheet. So I think that's not really the context. And there are also some points I didn't agree with the reviewer, is that in the experiment we use, in a geometric object experiment, we have used we use a stand to we use a stand, and the stand can rotate it, so we
we didn't really use contact the gas sheets. And I think in all the experience, you cannot really don't contact the gas sheet completely. So I think, in my opinion, if you don't really use a ruler to measure the gas sheet, I think that is reach the contest action. That's my opinion. And thanks for listening. It's all my remarks. Yes.
Okay, thank you. All three presenters, please go up to the stage. We will move on to the question of the juries. And I would like to ask all the juries, when you ask questions, please use the microphone in front of you. So, is there any questions? Please.
Two questions for the reporter. Yes. The first one is, when you use Bruce angle to measure the refraction index,
yes.
Clearness of the surface is very sensitive to the Bruce angle. Also, when the lens is thin, the second refraction is the birefringence of the material also affecting the reflection a lot. Have you considered this? Second question is, when you calculate the absorption, you only calculate the specular reflection and the direct transmittance. Then you did forget about the diffuse scattering. That would mean you will be underestimate the reflectance and the transmittance, so you will have a wrong absorption. Have you considered this case?
In absorption coefficient, we first use a Fresnel equation to calculate the refractivity when the incident angle is 0. So we have considered that. And
no, that's only specular reflection. You forget about the diffuse. Diffuse means the roughness of the surface, which will reduce the reflectance. Have you considered this effect?
Yes, thanks for proposal. And those are some error. Yes, sorry. Yes.
So you mean you didn't consider? I think that just yes or no.
Yes.
No, you didn't consider, right?
No.
And
about the first question.
The first question is, the cleanness of the surface is very sensitive to the Bruce angle. Also, the birefringence of the material will affect the second reflection peaks to have changed the correlation.
Yes. Actually, in the screen, in the Bruce angle, in my experience, we cannot really find the laser dots disappear completely, and I think that's the surface effect. Yes.
Okay. Is there any other questions? Oh, please.
Okay, I think that there's a major point, and I think the opponent and reviewer both mentioned is threshold limitation between the two methods the reporter has done. You use two different methods, and you find that one is for the thicker or thinner glasses is better than the other, right? The reporter? Yeah. Okay. I guess both of you point out, but could you tell us the answer? So what's the threshold limitation between the thickness?
Actually, we're not sure what the threshold would be.
Well, it just, or maybe when the glasses is too thin, then you probably use one method is better than the other.
Yes, because in their experiment one.
No, I just, maybe you can tell us the answer for that.
You mean the exact, the distance?
Well, it's just what's the mechanism, why you add, what's the relevant parameter?
We think that the glass shouldn't be so thin that the two laser dots connect with each other.
Compared to what thickness? You mean thin compared to what thickness?
Compared to what thickness?
Well, thin means it's thinner than some thickness. Then you.
We're not sure what it is in there.
So you don't have the answer.
Yes, we don't have the answer because this the thickness of the laser and other properties also affect this threshold. So it's impossible for us to know the threshold for them.
I think.
Actually, sorry, the reviewer.
I'm sorry, for their experiment I cannot give a direct thickness too, but I believe that the displacement should be bigger than the dots, the laser beams dots.
What should be larger than laser dot?
The displacement between the two laser beams. The displacement. The displacement.
Okay, how about reporter? I guess both of them challenge the issue. So you have better answer now?
Okay, proposal, I don't what you mean this.
Okay, you have used two different masters.
Yes.
Right?
Yes.
And you think if the glass is thicker, then one master is better. On the other hand, if it gets thinner, then the other master is better. So what is there's the reviewer said this is threshold thickness. And that thickness is what is relevant parameter related to that thickness?
I think the thickness as the absorbance or thickness.
I think you don't really have an answer, right?
Actually, I really get the point.
Okay, I think that. So, is there any other questions? Yeah, please.
Excuse me, just a technical, some doubts about some technical detail. Could a reporter turn to page 34 of your slide, please? Sorry, you have a slide showing the errors versus the thickness. You have a slide of error versus the thickness. That maybe the top one. Yeah, here, no, this is not the. If not 34, maybe 54, because you didn't really show your page number clearly. Excuse me.
Sorry.
Yeah, the lower one. 37, sorry. Yeah, the errors. Here, the vertical axis is the experimental error, and the points have error bars on it. So could you just briefly elaborate how do you get the errors on errors? Briefly, sorry. Yes.
The y-axis is already an arrow, but how can you have an arrow bar on arrow? So can you explain the arrow bar, the meaning of that? Or what's the meaning of your experimental arrow? Okay, you got that?
I think the error is from by measuring the relative parameter in experience, just like the distance between the screen and slits, or the distance between the streets. So I think the error is mainly from that.
Thank you.
Assistance.
Okay, thank you. So we move on to the scoring, and all three teams, you can have a seat. Okay, so please all the jury raise up your scores, and I will read from my right hand side. The score goes to, for the reporter is R 8, 6, 7, 6, 6, 6, 5, 7, 4, 6, 6. The scores for the opponent goes to 9, 8, 8, 7, 7, 7, 7, 8, 5, 7, 8. The score for the reviewer goes to 9, 8, 8, 8, 8, 8, 7, 9, 6, 7, 8. Thanks all. So we finish the first section, and I would like all three teams to change your seat during the break, and we will have a 10 minutes break.我可以提醒大家一下，我们楼下有餐点，那大家可以下楼去享用。然后，在我们办公室，在4天的竞赛期间，我们捡到了不少的东西，包含电脑的电源线、外套、杯子各种东西。如果你有弄丢的，或是你同学有弄丢的，请你到那个竞赛的办公室找我们，谢谢。
应该要够装到那个才对，应该3个小时大概。
Hello. Testing. Thank you.
Okay, I think the break time is almost end. So I would like to start the second section. Okay, the second section, the reporter will be terminator, and the reporting problem will be not problem number 1, lagging pendulum, and the opponent is Excel Pioneer, and the reviewer is Xiaomi Nassars. Is it? Well, I know you don't know how to pronounce it. Okay, now the reporter. Now you have 5 minutes for your preparation. The clock. 5 minutes preparation. Yes. So now the times start. During the preparation, I would like ask 3 teams to write down the presenter's name on the board.
Okay, I think I'm ready.
Okay, so we move on to the presentation of the reporter. You have 12 minutes, please.
Thank you. Today we are going to talk about the topic lagging pendulum, and we are the Octerminator. Now let's begin with our table of contents, and we will follow the following procedure to have a smoother process. So we can start with the introduction. It tells us that a pendulum consists of a strong thread and a bob. So when the pivot spins around, the bob will trace a lagging circle behind, which will have a smaller radius. This tells us to investigate the motion and the stable trajectories. So what is a lagging pendulum? Now we can see that we constructed a model which is exactly the description of the introduction. And we can see that the relevant forces interacting in the system will be the T, meaning the tension of the thread, the mg, which will be the weight of the bob. And so we can see that T sine theta, the theta being the angle right here, will be mr omega squared, omega being the angular velocity of the pivot. And the T cosine theta will be the mg. So if we arrange the equation, we can get the relationship between the angular velocity and the angle is omega equals this thing over here. And so because G, L, and the big R, the radius, are the already known constants, so we can know exactly the relationship between the angular velocity and the angle right here. So, because due to the limitations of the angle, we have a limitation of critical angle for a lagging pendulum to form. And so because we know that theta must be between 0 degrees to 90 degrees in order for it to be defined as a lagging pendulum, so we can get that G tangent theta will be a positive number. And so therefore, L sine theta minus R should be a positive number for the angular velocity to exist. And so therefore, we will get the result that sine theta will be greater than radius divided by length. And because the maximum of sine theta is 1, the length will be greater than must be greater than the radius. So let's continue. Because there are the limitations of the mathematical equations, so we want to use the intuitive understanding of this limitation. So what this equation is saying that the pivot and the bob must be on adjacent sides for it to be a lagging pendulum. And so because in this graph, the thread tensions points this way, and the centripetal force is pointing to the center, so the thread tension can provide the centripetal force. However, when the bob and the pivot are on the same side, the thread tension could not provide the centripetal force that it needs. So it is impossible for this situation to form a stable trajectory. Now for the second question, we are wondering what makes a lagging pendulum. So once upon a time when the length is not greater than the radius. So if we look at the equation here, we know that the angular velocity will not exist. And so therefore, it will be only stable in the normal state. And we define the normal state as the bob having a larger radius than the pivot. However, when the length is greater than the radius, both states could exist. So there must be a connection, or rather say a transformation, that we can go from one state to the other. And so if the transformation is to happen, the acceleration is the key. And why I say so is because if the pivot changes the speed, well, either you make it faster or make it slower, the bob will responsively lag behind or advance in front. And so the greater the mass of the bob, which it will have a greater inertia, and the greater the air drag, the lower angular acceleration we need for it to transform into the other state, meaning transform from a normal state into a lagging state, or transform from a lagging state into a normal state. So this makes it a lagging pendulum. So according to the theory, we made some parameters that we would like to test about in our experiment. First one being the length of thread, second being the distance between the pivot and the center, the radius. And the third one, the pivot angular velocity, omega. And so for experiment 1, we are to prove the model is correct. So according to our parameters, we point our experiments over here. And so for the equipment, we have a stepper motor that could control the exact angular velocity. And we have an Arduino board to control it, of course. Now this is the rod that we marked to have our bob hung above, and this is the strong thread that we have. So for the first experiment, it is about the length of thread. So according to the equation, we know that when the length increases, then the critical angle will decrease. And when the angle is fixed, if the length increases, then the angular velocity will drop. So we experimented with the length of 20, 30, and 40 centimeters. So this is our result, and we can see that it falls perfectly to our prediction, so it is qualified. And for the second result, it falls perfectly to our second assumption, so it falls qualified as well. So for experiment number 2, we test about the distance between the pivot and the center. So if we look at the equation, we can expect when the radius increases, the critical angle will increase as well. However, when the angle is fixed, if the radius is increased, the angular velocity will increase. So we tested with 1, 3, 5, 7, and 9 centimeters of radius. So this is our result, and as usual, it falls perfectly to our prediction, so it is qualified. And for the second experiment, it falls perfectly to our expectations too, so it is qualified. Now, because we have 5 groups of experiment group in this experiment, but we only show 3 results. So what about the 7 and 9 centimeters? Well, we can discuss that later. For the third experiment, we have the pivot angular velocity. And so because looking at the equation, we know that the angular velocity directly affects the angle. And so we must have a relationship between the angle and the angular velocity. So our experiment group will be 30, 60, 90, 120, and 150 rounds per minute. So let's look at the theoretical graph. So according to the theoretical graph, this is the according frequency, which is the angular velocity times frequency times 2 pi is angular velocity, and the angle. And so the first thing we see that there is missing angle that does not have a qualified frequency, and that is because the sine theta has a limitation of minimum of being greater than radius divided by length. And the second part we notice is that for the same frequency, we will have 2 stable angles. So what will happen? Now, if we look at the, according to our experiment, when we have 30 RPM, it will fall right here. For 60, right here. And for 90, 120, and 150, it will fall right there. So we can expect that for the 30 RPM, there will be no according angular velocity that could make it turn as a lagging pendulum. And for the 60 RPM, we could know that there will be 2 very close velocities that could make it happen. And for 90, 120, and 150, there are 2 angles that could make it stable. So this is our experiment. As we can see, the 30, 60, 90, and 120 is according to our prediction. However, for the 150 RPM, it's unstable as well. So why is that? Now, for the first point, why does 190 and 120 only express one angle? And that is because things in the universe tend to stay in the lowest energy state. So if it has two stable angles, then it will stay in the trajectory which has the lowest potential energy. According to this graph, we can see that if there is two angles that is possible for the trajectory to form, then it will stay in the theta 2, but not in the theta 1, because this one has a lower potential energy. So what about 150? Well, we can discuss that later as well. So for experiment 2, it is about the transformation process. And the transformations happen because we found out that the critical angular acceleration is inversely positively related to the weight of the bob, meaning that the greater the weight of the bob, the less angular acceleration we need. So however, when the angular velocity reaches a certain level, the system becomes unstable. So it becomes unstable, and unstable meaning that it could not stay in a lagging state. So we do not know the correct relation or the exact relation in the two variables yet. So in conclusion, first one, the model is applicable under certain limitations and scale. Second of all, the trajectory of the bob is generally a circle with the radius of L sine theta minus radius. And the third one, only one angular velocity exists for each angle, even if theoretically there could be more. So this is our reference, and thank you very much.
Thank you for the presentation. So we move on to the question from the opponent to the reporter. The time is 2 minutes.
Okay, first I really want to ask, what is your setup?
What is my setup?
Yeah, how did you do your setup?
How do I do my setup?
Yes.
So,
and in your setup, you must use a motor, right? That on the top to turn the.
I did use a motor.
And how is the power of the motor?
The power is powered by a DC.
No, I mean the power.
Okay, so you want to know about the motor. So this is the stepper motor we have, and its maximum accuracy is 1.8 degree. The working voltage is 5 volts, and its maximum velocity that we can reach is 3 hertz.
Okay, and the next question will be, is the thread tighten?
Is the thread tighten? Yes. Okay, so according to our theory, we used a rigid rod. However, we also used a soft rod as well. So which one are you asking?
So you are using a rod instead of a line?
Because due to the introduction, it talks about a strong thread. So there are two meanings of strong. One meaning that it's rigid, one meaning that it does not deform easily. Yeah, so we did both experiments. So which one do you want?
Have you done it with a line? Like
yes, a soft rod. Yes, sure.
A rod or a line?
A line, a soft line, meaning made in cotton, or maybe in plastic, or maybe in metal.
And under what condition there will be a smaller radius?
As I just said, the condition for our model is that if it fits our equation, that it could. However, there are certain limitations. So are you asking about...
Okay, I'll discuss this with you later.
Okay, the time is up. So the following is the preparation of the opponent. You have 3 minutes for your preparation. So the opponent, you have up to 4 minutes for your presentation, and then up to 40 minutes to discuss. Please.
Good morning. We're the opponent of this round, and we're from Team Excel Pioneer. And okay, and this is some short question that we asked when we discussed in the short question. First, we asked about the power of the motor, because we believe if the power of the motor is too low, then maybe the motion of the pivot can affect the rotation speed of the motor. And when we asked that, did you make sure that your thread is tightened? And the reporter stated that he both used the tightened thread and the soft thread, so which believe that is very good because he's considered both kind of conditions. And this is a reporter's point. First, he's using a constant speed circular motion to build his own model and to try to explain this phenomenon. But how we believe is that this is not stable. That maybe it can, it's not a stable circular motion. And the reporter has stated that there is a normal state and a lagging state. And because the air friction is about the mass of the pivot and the speed, and which I didn't see the reporter has considered the air friction into his model. And about the setup, that he has used a motor that is a stable motor, which he can control the rotating speed, which we believe it must be accurate because you have a thing to control the rotating speed. And the data is that he has tried to compare his parameter and try to discuss, according to his theory, how this parameter can affect the motions. And then this is for a reporter that his theory is that he has a very clear model and a very ideal setup. But from our opponent's view, we believe that your setup is too easy because you consider it as a circular motion, and which we believe it isn't. It isn't that simple. And the reporter hadn't shown the trajectory of this motion, which he just keeps saying that it's a circular motion. And as like what I have stated before, that we believe this is a very unstable situation, that it couldn't reach a stable condition. And about the setup, because I would like to discuss about the setup because the power of the motor, I think, is the most critical part about this experiment. And the strong thread it could affect the results because it could affect how the pivot will move. Then the weight of the bob that the reporter hasn't measured in his presentation. And there is some about the measurement. We think that because the reporter didn't say that how he measured the entire motion, so we would like to discuss it later. And about the theory, because it will be very sensitive to the initial condition, and the bob can move in a three-dimensional system, and the trajectory will be limited by the length of the string. So the opponent believes this motion is a chaos. And I would like to skip to the next phase.
Okay, now we will move on to the discussion.
Okay, first is about your setup. Can you show me how you set the entire model? No, how you do your experiments.
Okay, thank you. Thank you for your suggestion, though, and I do have a video for you.
And how did you measure the entire? Oh, okay. So where is the motor? Is on the top of that? The motor is here.
Yes, it is.
Wait, what is this? This is a stick or line?
That's a rod, meaning a rigid rod.
A rod.
Yes.
So it won't deform things.
Even if it is a thread, because it should be strong. So according to definition,
what would it be if you change it?
Yes.
in your model, the only force that pointed down is gravity. So if you use a rigid pod, it can push the bob downward, and you didn't fix that in your model, correct?
As I mentioned in my conclusion, there are certain limitations and scales. So I was wondering if you are asking about the limitations.
But in here, you say the trajectory is
generally a circle.
Generally a circle. So did you have any graph about your trajectory?
Yes, I do. But do you want to understand?
Can you first show it to me? Because I would really like to see it.
Okay. Well, because you still want to see it, so here it is. And
so it just keep doing circles. And and is this a circle motion or it's just spinning around?
Could you please let me explain my limitations of the model?
Okay.
So, because I want to speak so eagerly because it will influence the outcome.
So please explain.
So, the limitation of the model is because we did not consider the air drag in the model. And the air drag is defined that a force acting opposite to the relative motion of any object moving in the surrounding fluid. So for example, a plane or a race car. So if we use the drag equation, we can get the drag that we need. And so the rho is the density of fluid, the v is the relative speed of the object, the CD being the drag coefficient, and the A is the area of impact. So if we estimate the drag in our experiment, the P in the air is basically 1.225 kilometers per m cubic, and the CD is the 0.45 for a smooth sphere, and for the area of impact, it will be this. So what we get is a very, very, very small drag. And so if we look at the graph of velocity to force, we can see that it barely moves in the first part. So if we have to consider the drag, then we would have to put the drag in the picture, and therefore our tension must move to over here so that it can provide a tx-ty, and the ty could balance out the drag. And so when the tx is smaller, then the centripetal force, so making it having a smaller radius. So the radius that we tested will be slightly, very, very slightly smaller.
For a second. In this picture, when your tension force will pull the pivot away from the balance point, correct?
It is to be stable, then yes, it should look like this.
So then it will reach an unstable condition.
Why is it an unstable condition?
Because it isn't at a balance point. The balance point should be across the center of the circle, then the pivot should be over here, so it can reach the stable condition. Is that correct?
So in your definition of balance point, you mean that the pivot and the bob must be on exactly adjacent sides.
Yeah, so then it can be in the same speed, and the angular velocity will be the same.
However, if you look carefully at this graph over here, because this providing the tension, it could also provide the centripetal force it needs and the force that could counter the air drag. So although it has a smaller centripetal velocity, centripetal acceleration, so it will drop into a lower radius. It will still be a periodic motion, and so I consider that as stable. Do you?
But the farther it gets away, the force, the balance point will be, it will be much far away from the balance point, and the force will put it much more further away.
Yes.
So how can it be stable if it's just keeping going away?
Yes, so I'm not done with my limitation.
Okay.
So if we look at our PPT, So we want to talk about the source of error because in reality there are numerous sources of error. And so due to these errors, they will result in a so-called unbalanced state. But generally, it still would look like a circle.
And wait, so this is the source that you can cause the error of your model?
Yes.
So if you try to consider all this error into your model, how will the trajectory look like?
Okay, to answer your question, because in the reality experiment, yes.
So sorry.
Because in our reality experiment, the reality considers all the forces. So the results we get from reality is the trajectory that it will if it is having all its errors. So as we increase the angular velocity, it will become kind of a stable trajectory, and then it will be messed up again. And if you want to talk about chaotic motions, then we can talk about that. Would you wish to do so?
So, yes, sure, why not?
Okay, so a chaotic system is that, so to define chaos, we define it as, actually someone else.
So sorry, can we just skip to how chaos is related to your motion?
Okay, so because the chaos system must be sensitive to the initial conditions,
yes,
and the interacting forces during the process is in constant, meaning that for every second, the friction forcing on the bob, for the slightest change in the flow of air, for example, if you sneeze, then it will change the slightest amount, and if there's a slightest amount of change, it will change the whole thing.
Yes. So did you think that it really affect your model if you consider chaos into your model?
Okay, so we can look again at our conclusion. And in our conclusion, it talks about the limitation and scale. So you just talked about scale. And so in grand scale, excuse me, to our naked eye, we can see that it is a circle. However, if we trace the trajectory of the bob, it will be chaotic because we are in such a minimal scale.
And how did you trace the track of the bob?
Okay, so we put a recording device.
So like a camera on the
yes,
bob?
a camera, and below the bob, and we use tracker to track, and because tracker has to define the axis, the correlation, and how because to our to our.
Just keep talking now.
Okay, so you're listening. Because if you have you are further away from the camera, it looks smaller. Yes. So we put a ruler at the height of where the bob will be to make sure that we have the correct units for how the bob moves.
The motion of the bob is supposed to be 3-dimensional, not only 2-dimensional.
Oh yes.
So the bob will go up and down.
That is not necessarily true.
Okay, so have you ever considered this phenomenon into your measurement?
So are we talking about our experiment or your phenomenon?
No, it's because you're filming the motion.
Yes.
And this phenomenon can be observed when you have, it's about...
Sorry, the time is up, so I have to
Thank you very much.
So we move on to the concluding. The opponent make a summary of the discussion.
Okay, and in our discussion, we basically keep on talking about how to set up his device and what kind of theory he used, and basically the opponent think this is an unstable condition. So basically, his model cannot be used because the model doesn't explain anything, and the air drag is. The opponent thinks that air drag is a very big error that he doesn't if it doesn't consider the air drag, it must be a very big error. And the model is too simple to explain everything, basically nothing, because this is a chaotic motion. Thank you.
Okay, so we move on to the question of the reviewers to the reporter and the opponent, please.
Okay, so first off to the reporter, I have a simple question. Can you define stable?
Okay, there are two ways of defining stable.
Sure.
One, to the grand scale. If we see that it's a periodic circle
So you use
motion,
your eyes to see if it's
yes,
stable?
the grand scale,
Okay.
it's a circle. If you use a minimal scale, then it will be unstable because it's chaotic. Thank you.
So your trajectories were not stable because they were chaotic?
There are two, as I repeat, there are two.
Okay. So to opponent, can you define stable? Do you have a better definition for stable?
If it is stable, it should be turning in the same speed.
It should turn at it.
Yes, it's angular.
Okay, so to the reporter, how do you know that a uniform circular motion is the only stable trajectory?
Because according to the introduction,
you assumed that it was uniform, like it was a circular motion from the very start. How can you assume that?
excuse me, what, can you make your point again?
Like you assumed from the very start that it was a circular motion. Like how can you assume that it's a circular motion?
How do you know that I assume it from the very start?
Oh, okay, then please explain.
Okay, so in the very start, it will take some time for it to become into the stable trajectory that we define.
Like in your model. Like in your model.
In model, it has already reached the so-called stable state.
Like,
so do you want me to explain how it transformed into?
No, I don't want you to explain. Like I want you to explain why it's a circular motion. Like why can't it be like a line or some other shape? Why does it have to be a circle?
Because according to our model, if you have pay your attention, we have only the centripetal force that will make anything, an object which has a centripetal force will make it move in a circular motion.
Okay, did you control the initial conditions of your experiments?
Control the...
Like from the very start, how did you start making the pendulum move?
We have two kinds of, you mean the initial condition?
Like how did you start, like from... When you started turning the pivot, did you make sure that the bob didn't move, or did you just let the bob stay there? And like...
Of course not. There are two ways of starting the initial condition.
Yes.
One being it hung down from the pivot and it does not move. One being that we control it first in the middle and then we will make the pivot.
Was there a difference?
Yes, in fact there is a difference.
Did you put it in your PowerPoint?
Because that is not relevant. Because if you have listened to my presentation...
You said that this is chaotic, so it depends on the initial conditions. If you say the initial conditions are not relevant, then why?
No, you did not get my point. Because in my error, there is the other forces in...
Okay. So does the pendulum immediately start lagging, or does it like, first is it, like what is it at the very start? Like is it lagging, or what other form does it take? Like in your experiments, like before it becomes lagging, is there any special phenomenon that happens before that, or?
Sorry, the time is up.
Thank you.
So the reviewer, you have 2 minutes for your preparation. Okay, now is the time for reviewer to take the floor.
Thank you. So I'm the reviewer for this physics fight, and I'm from Team CO Minnesota. And today we're going to talk about problem number 2, lagging pendulum. Okay. So here's the problem statement. We're asked to investigate this phenomenon where if we put a bob at the end of a thread and we rotate the pivot, the bob should start rotating at a smaller radius. And we're asked to investigate relevant parameters that may affect this phenomenon. So first, this is my outline. So I'm going to start off with the reporter's summary. So first off, the reporter gave an ample explanation of what the phenomenon was and showed us how the bob may trace a smaller radius. And then he went into, he talked and showed his theory and how the bob should move when it's in a lagging state, and gave us a very simple model. And then he went into his experiments. He changed the string length, he changed the radius of the pivot and the angular velocity of the pivot, and found that his results completely matched the theories. However, we have some suggestions and some things that he should improve on. So first off, he had a very good model, and in his report, he did not clearly define lagging, nor did he clearly define stable. Also, he did not give a model of a model when the string is not completely straight. And also, we believe that 3 dots does not mean that your theory completely matches your result. 3 dots is, well, 3 dots. Then also, we believe that the reporter should consider the initial conditions because they believe, well, the reporter and the opponent believe that it was chaotic, and they think that the initial conditions don't matter for some reason. And also, we don't think that the reporter fully explains why there are two theoretical tracks the bob can turn when in reality there's only one possible explanation or something like that. So here's the opponent. So the opponent, in his questions, he clarified his setup and clarified the models and the theories of the reporter. So this is some suggestions we want to give to the discussion as a whole and to the report. So yeah, so I'll just talk about the red ones because I don't have enough time. So first off, we believe that the definition of stable is very, very important, and we believe that is one of the main things that they did not talk about in their discussion. And also, in the reporter's report, we believe that the locuses that they tracked were, well, not stable, and that does not fit with the problem statement. And also, 3 points is not enough. I cannot stress that enough. We believe that more experimental data is needed to prove that your results match your theory. And here is their discussion. So first off, the opponent asked about the limitations of this theory, of this model. And the reporter talks about there are certain limitations because there are other forces acting upon the bob in reality, and like, for example, air drag, and it's very important. However, the reviewer believes that you did not calculate the air drag and other forces, and you did not match your theory with your results. Then opponent asked about the locuses, that this is very unstable, and the reporter keeps talking about the sources of error. And again, we believe that they did not talk about the definition of stable, and we think that that is one of the most important things that they did not talk about. And then the opponent asked if the opponent says that this is a chaotic motion, and then the reporter talks about initial conditions. However, he believes that initial conditions are not important, and we don't think that, and chaotic motion is not stable. So then the questions I asked, first off, I asked them to define stable, and the reporter says we use our eyes. If they move in a circle, then it's stable. And we believe that this is not the definition of stable. We think that the definition of stable is when the energy level stays the same, or when the energy changes at a periodic rate. And also, then I asked, how do you know that the only stable condition is the circular motion? The reviewer says it just is, centrifugal force or whatever. And the reviewer believes that you would need more explanation to prove that, yes, this is the only motion that is stable. So then I asked, do you control the initial conditions? And the reporter says they don't matter, and okay. Then I asked about if the pendulum immediately starts lagging, and then what happens before it starts the lagging phase. The reporter doesn't have time to reply.
The time is up.
Yeah.
Thank you.
Thank you.
Reporter, you have 2 minutes for your concluding remarks. Thank you for, please.
Thank you. So I would like to give a word of advice to the reviewer. Maybe you can slow down and listen to our presentation and speak slowly so we can understand more. Thank you very much. So to answer the last question of the reporter, I think we are talking about the spherical aberration. And we think that the change of the spherical aberration is very, very subtle if you consider it. So we did not think that it is significant. So thank you very much. And also to stress how subtle the air drag is, we can go through it swiftly again. So we calculated the estimated drag, and in fact it is very, 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 very small. And so we did not put it in our model because we think that it doesn't have that significant effect that other components may have in our model. And also to define our to make our definition of stable clear, which I think I said 3 times in my presentation. However, the reviewer still asked, is that because in the introduction it talks about a circle, but nothing moves in a perfect circle. So we can use our naked eye for a grand scale of the circular motion. However, if we look closer and trace the exact trajectory, then we find that its movement is actually chaotic. And so that is our 2 definitions for stable. And to conclude this up, thank you for the opponent for asking such detailed questions, so we can know that what I'm missing, and thank for the reviewer for such a fast speech. Thank you very much.
Thank you. All 3 teams, please get to the stage. Get prepared for the question from the juries. So, are there any questions? Yes, please.
Okay, very interesting debate. But it seems to me the discussion went a little bit chaotic.
In fact.
Okay, maybe let me start from the opponent. You mentioned about it should be chaotic. So why do you think it's chaotic? And what do you mean chaotic?
Based on my knowledge of chaos, because there are 3 conditions. First is the initial condition of the motion, and the second is the boundary, and the third, and this is a 3-dimensional. And so we believe that because the air friction and some of the parameter that he doesn't consider, that he believes that it only cause error, that we believe it will affect the initial condition, so it will cause a chaotic motion. And because of the length of the string, so it will be a boundary. The place it moves is boundary. Yes.
Okay. So you just assume it's chaotic. So it's chaotic.
Based on his report. Yes.
Okay. The report. Would you show the page 59 your results, please? Okay. What's the difference between these 4 figures?
So, thank you.
Please be short.
To answer this question, these 4 are moving in different angular speed, being the one on the left top the lowest and gradually being larger, the angular velocity of the
What's the difference between these 4? The angular, I know there are different initial conditions. What's the difference between these 4? You start with this slower angular velocity, or what? What's the difference between these 4?
So in this case, we used a XY graph to analyze whether it's chaotic or not, which if we consider it's chaotic, then it will have
Sorry, for example, the first one.
Yes.
I mean, what's the difference between
So what's the different angular velocity you start for these 4? The 1 hertz, 2 hertz, 3 hertz, 4 hertz, or something like that? Please answer.
In this case, we used our voltage as our controller.
Yeah, so give a number.
Okay, this is 5.5 volts, that's 6 volts, that's 6.5 volts, and that's 7 volts. And we use this for our preliminary observations of how it would actually move. And then we step into our exact experiment.
5.5, 6, and so they're very close.
Yes.
So you put these 4, you try to show they're in different modes. I mean, you
Oh, yes,
these
yes,
4.
yes.
So briefly tell us what the difference.
We have a limited time, so please.
Okay, I just try to straighten out. I mean, whether it's circular may depends on your initial velocity. So since you show these four figures, they must. I try to tell us there are different modes. It depends on the initial velocity or angular velocity. I just try to straighten out that part.
Yeah.
Okay.
Your answer is the initial velocities are all very similar for these four.
So according to the reference in the reference kit, it talks about that when a damped force pendulum, it will have a chaotic motion.
I think just the jury just want to clarify the
my
point.
bad, sorry.
So is it okay? So are there any other questions? Yeah, please.
Reporter, could you please turn to page 15 of the slide, please?
Page 15. Not this one?
Yeah, the greater the mass of the board and the greater the air drag, the lower angular acceleration needed. Are you really sure that the motion is dependent on the mass?
Because we consider that if we increase the angular velocity on the pivot, then because the greater the mass of the bob, the greater inertia it has, so it is on tendency to move accordingly to the pivot.
Since if the wheel is driven by motor, then the only acting force is the gravity, which gives an acceleration independent of mass.
Yes.
Okay. Thank you.
So are there any other questions? Yeah, please. Could you use the microphone?
When you go to the theory, the part, you make a chart of the living pendulum. You mentioned there is a mass, the mg downward on the ball.
Yes.
Right?
Yes.
That means you don't have mass. It's massless for the string. Is what you mentioned here?
Because we in the error there should be the form of the string, but in the experiment we did not have such a great mass that will deform the thread.
How do you think about the theory setup? You have a massless string, and you will have a smaller radius r. How do you think about this?
The opponent believes that if from this picture, I believe the report only considered the pivot as the center of mass, and because when the motion is happening, the pivot might turn, so it could affect his theory.
Yeah. How about review? How do you think about R and mg, small r?
Well, so first off, I think that I agree with the reporter that the string is a little too light to be taken into consideration. But however, I think that they should do experiments to prove that the string really, like the weight of the string really won't affect the results.
Okay, yeah, please.
Excuse me. For asking one more short question, sir. Could a reporter turn to page 44 or 45? Yeah. This formula gives the air drag, which is proportional to the velocity squared. But and this formula applies when the Reynolds number is large. And there's another formula, which is the so-called Stokes formula, which gives an air drag proportional to the velocity, which applies to the case of when Reynolds number is small. And are you sure that this formula really applies to your case? Is it applicable?
Because according to our research, our sphere has the Reynolds number of 10 to the 5th power, so we consider it as a large Reynolds number.
Reynolds number is not the Reynolds number of a body, it's the Reynolds number of a flow, of a fluid flow. Okay, that's okay. That's only one point which I want to clarify.
Yeah, okay, thank you. So are there any other questions? Okay, if there's no other question, we move on to the grading. Okay, the marks for the reporter goes to 7, 6, 6, 8, 8, 8, 7, 5, 5, 8, 7. The marks for the opponent goes to 8, 8, 8, 7, 6, 6, 6, 7, 4, 7, 7. And the marks for the reviewer goes to 8, 8, 8, 8, 7, 7, 8, 8, 6, 8, 7. So I think the grades we have some pretty low marks for the opponent. So can you give some comment about the form?
I think they did a good job, but basically the original rock is pretty big to me. So it should look like a physical pendulum instead of a simple pendulum. And also there's another thing is the trajectory they were showing is basically not a uniform circular. So it would be very difficult to define what's the exact radius and the angular frequency would be. So this is the point that I think they didn't do a great job in here.
So now, yeah, please.
Although my grades, my score for report is not a single, but it is among the lowest. But so I would like to explain briefly. I agree with the reviewer that your theory is only qualitative. The prop on slide page 22 of 23 show only 3 points, and you do not have any theoretical curve to fit the points. And so this gives the overall impression, and it is also the theory is only qualitative, no quantitative theory. And also, please don't use the discussion time as an extension for your report. The opponent also has some responsibility for that. Okay.
Yeah, I think opponent, you should stop him to continue your discussion. Yeah, anyway, we have a very exciting discussion in this section, and I would like to announce a 10 minutes break. So please come back in 10 minutes. Thank you.
不用像外国人，永远不可能像外国人，除非你像我这样。要像你现在想要练那个节奏太难了。你是有多大的？ 对。我是维纳斯。现在是看你们。我没有。
喂 ，hello， testing。
Okay, it's almost time, so I would like to ask all the participants and the audience to come back to the stage. And the third stage, the reporter will be Excel Pioneer from 协同中学, and the opponent will be Xiaomei Nisai Lei from Kaohsiung 中学, and the opponent will be Arc Terminator from 新竹科学实验中学. Okay, the problem they choose is the magnetic train, number 5. So we start from the preparation of the reporter. You have 5 minutes for your preparation. During the preparation, please 3 teams write down the presenter's name on the board. Thank you. Okay, before the presentation, I will make a short announcement that we will have a award section after the third competition. So please, I would like to ask all the audience and all the participants do not rush out after the competition ends. Yeah, thank you.
Hello?
So now we move on to the presentation of the reporter. You have 12 minutes, please.
Good morning, I'm a reporter of Excel Pioneer. Today I'm going to report a problem, magnetic trend. This is my presentation outline. First, I will show you the phenomenon and the theory and calculation I made, and then I will do some experiment and will make a conclusion. So this is the problem statement. Bottom magnets are attached to both ends of a small cylindrical battery. When placed in a copper coil such that the magnets contact the coil, this trend starts to move. Explain the phenomenon and investigate how relevant parameters affect the trend speed and power. So this is my observation video. As you can see, here is the copper coil, and I inserted some thick paper pieces in each gap of the coil to stable the turn density. And through the gap, you can clearly see that the trend had power itself to go through the whole coil. And this is my theory. Because of those two magnets, the trend itself will generate a magnetic field. And because when we put in the coil, the magnets will contact the coil, so the battery will form an electric circuit, which means there will be a current inside the coil. And that means that the trend's power is come from the battery itself. And so we can know that the coil will get a force which will be an integration of I times d L cross B. And according to Newton's third law, the trend itself will also get a counter force which has the same value but in the opposite direction. So here, to calculate the force, I put the center of the coil in the center of the YZ plane. And if S means the gap between each round of coil and N is the turn density, we can know that the S will equals 1 over N. And if we define the angle theta, and we can get this point's position x, which will be theta divided by 2 pi n, and y will be r cosine theta, and z will be r sine theta. And if we turn delta theta, then we can define another point, so we can define a vector L, which we can calculate by minusing the 2 points position. So here, let's look at the magnetic field. We can separate the magnetic field into two components, one vertical to the x-axis and the one parallel to the x-axis. And when we look at these two directions of magnetic field, we can know that the vertical one will generate a force that pushes the trend to go forward, and the parallel one will generate a torque, which I will talk about it later. And since the vertical one is the one that pushes the trend, I'm going to focus on this one first. So since the magnetic field should be symmetrical around the whole trend, I believe that the magnetic field can be described as a function of d and x, which d is a vector that vertical to the trend surface. So to calculate the d vector, we can first set the small r, the radius of the trend, and the center to the coil, and the distance between these two centers will be big R minus small r. So now we can calculate the direction of the d vector, and then we can simply calculate the d vector as the value of it times its direction. And now, so we can rewrite the vertical magnetic field into its value times its direction. So we can rewrite the force the trend gets into IBL plus D, and it will be written in this equation. And now, since the force that pushes the trend should be in the x direction, so we can simplify this equation into that the force that the trend gets in the x direction should be equal to the current times a function of some geometrical parameters and times the magnetic field. And so what I do is that I add up all the L vectors through a whole coil, and then if the delta theta is very close to 0, it will be as like the reality situation. And if L means the distance between those two magnets, then we can know that the amount of the L vector should be equal to 2n pi L divided by delta theta. So now, let's look at our equation. We can know that the force that the trend gets will be proportional to the current, and the amount that the force it gets will be proportional to the turn density. And now, what we need to get is the value of the current and the value of the vertical magnetic field. So, to measure the value of the current, I made the battery put in a short circuit situation, which I put a wire into a circle, and I used Gauss meter to measure the magnetic field inside the circle. And by these two equations, I can calculate the current by using the value of the magnetic field. So this is the result I get. And by calculation, I can get that the maximum current that my battery should produce is about 3.5 ampere. Later, I measured the vertical magnetic field around the whole trend by using a Gauss meter. And I measured it with a gap of 2 millimeters, and in the d direction, I also measured with a gap with 2 millimeters. So I measured the whole magnetic field around the trend, and then it is the result. And this is how the x-axis related to each part of my train. As you can see, in the two ends of the train, of the magnet, the volume of the magnetic field is the biggest and in the opposite direction. And here I write a program to do the calculation for me, which delta theta is only 0.001 radius, and this is the code. And here are the conditions I input to my program, and then it calculates the force that the train should get, which you can see the force in the x direction is the biggest, and the other two are negligible. So by Newton's second law and some parameters I get from measurement, I can know that the acceleration that my train gets should be about 3.9 meters per second squared. So to check is my calculation alright, I do an experiment which I use a copper coil, and I connect a light string at the bottom of my train, and I let the string go through a pulley. And this is a device that I made to help me wind the coil. And here is my setup. So what I do is I film the motion of the mark, and then I can get the velocity of the train inside the coil. And here I get two types of result. And the why that makes this difference is that when the train is moving in this direction, and to get this kind of torque, that the torque versus the velocity will point up, it will form like the one in the left, which the velocity of the train increases smoothly. And for when the situation like the torque versus the velocity will point down, it will form like the graph on the right, which is free and stable and hard to analyze. And because I did not see a terminal speed in my experiment, so I decided to discard the acceleration instead of the power. And so why I think I make this difference, because when the train is going in this direction and it gets this kind of torque, the normal force against that is really small, so it will just get the normal friction. And if the torque is in another direction, it may easily bounce into the gap of the coil, so it will be stopped by another force, so it will be free and stable. And the acceleration I get from experience are in these two numbers, and as you can see, both of them doesn't fit my calculation, so that means I must have missed something. So let's look at our equation again, and you can see that in the middle is just some mathematical calculation which should be correct. And for a magnetic field, since we are using a natural magnet, so it should always be there, which is stable. So I believe that the problem is happened on the current. So to measure if the current is stable, I measure the voltage by the two ends of the coil, and this is the result. And as you can see, this at the bottom is the condition that the train is not moving and the voltage is stable. But when the train starts running like this on the top graph, you can see that sometimes I can get a voltage, but sometimes there is no voltage at all. So that means that when the train is running, sometimes the coil will be electrified, but sometimes not. And by calculating it, I found that the time percent that the coil actually get electrified is only about 1/3 of the time. So what I should do is that I should times the acceleration by my calculation, I get t%, which it will fit my experiment result. So if we look at our theory equation again, we can know that acceleration will be proportional to the current, and the bigger the turn density is, the bigger acceleration it will get. So let's do an experiment. So I try to change the current inside the coil by adding some extra resistance, which I use a carbon slide in different thickness. And this is how I put the carbon slide between the magnet and the battery. And this is my result. As you can see, the red line is my calculation result, which I have an error of 4.8%, and the blue dots are my experiment result. And as you can see, this is the condition when the train does not have any extra resistance, and after I add some carbon slides, the acceleration will be in this part. And as you can see, it will be proportional to the current. And I try to change the turn density by adding different thickness of small paper pieces. And this is the result. As you can see, the bigger the turn density is, the train will get a bigger acceleration, like my equation. And later, let's look at the radius of the coil. So, as you can see, if the R is bigger, the D will become bigger, and in your magnetic field graph, you can see here is the D, which if D is bigger, it will have a smaller magnetic field. So we can know that when the radius is bigger, the acceleration that the train gets will become smaller, and here my calculation fits my experiment result. And later, let's look at the magnetic field, which I believe will not be only generated by the two magnets, because the battery itself must have a big permeability to attract those two magnets. So what I do is I replace the battery with a wood, and this is the part that the train actually get an acceleration. And here you can see that in the middle part there's a difference between the wood and the battery, which this part actually takes 34% of the train's acceleration. So I believe that if we want to change a battery, we need to consider its change on the magnetic field, which will be not negligible. So as a conclusion, we know that when the magnetic field is bigger, the acceleration that the train gate will become bigger, and the magnetic field will not only be affected by the magnet but also the battery. And the battery itself will generate a current that power the train, and it will be proportional to the train's acceleration. And if we look at the coil, the smaller the R is, the bigger the turn density is, the train will be bigger acceleration. And by these two equations, we can change the acceleration into the speed and power that the problem statement asks us to investigate. And when we are doing this experiment, we should always make sure that the torque process velocity is pointed up, so it will get a lower friction. Thanks for your listening.
Okay, thank you for listening. Opponent, you have 2 minutes to ask questions. Start.
Okay, so the first question for the reporter. Do you change the batteries every time after you do the experiments?
No, because the new battery is not really stable. What I do is I use the battery that is stable voltage that I measured is about 1.47 voltage. So I use the voltage and I use the battery after I measure the voltage of the battery is in that value.
Okay, so did you mention the friction that the train when the train moves in the coil?
Yes.
Okay, so do you think there are any other forces except friction as in the drag force?
As
like stop the train. Stop the train moving.
I think there's friction. Yes.
Only friction.
Yes, I think that's the main thing that we need to consider if we want to consider the force that will slow down the train.
Okay, so do you think the torque is big enough to make a train like tilt like such a big angle?
I believe that no, because when I'm watching the train, it doesn't really flow out. But I believe if we want to do that, we need to calculate it by the parallel magnetic field. But I cannot measure the closest parallel magnetic field because my equipment is disabled.
Okay. Yeah. Okay, so I get your point. And do you think the magnetic field in the copper coil is homogeneous?
Sorry, what is homogeneous?
Homogeneous.
Yeah, what does that mean? I don't know.
All the same. The magnetic field is all the same in the copper coil.
No.
No.
If you were talking about a whole coil.
Oh, okay, I think that's all.
Okay, opponent, you have 3 minutes for your preparation. Okay, the preparation time is up. Please, the opponent, please take the floor.
Okay, so hello everyone, I'm the opponent of the team CLMSI today, and I'm going to talk about the problem for magnetic train with a reporter. And then first, let's take a look at the problem statement. So the problem statement asks us to place two magnets, attach both ends of a small battery, and then we place it in the copper coil. And then we want to investigate what parameters will influence its power and speed. Okay, so let's first take a look at the summary and comments for the report. So the theory, he gave us complete calculations about what the force that the force act on the train when passing in the copper coil. And then in the setup, he used small pieces of paper to control the line density, control the turns density, and I think that's really good. And I think his experiment of this parameter will be really, it will be accurate. And I think the parameters he did is the diameter of the coil and the turns density, and then the experiment he investigated about the velocity, and then it's his results. Okay, so and this is his advantages. So he completely analyzed the force acting on the magnetic train, and then he showed us the clear diagrams that shows the trend of some of the parameters, and then how about, but I think there may be some other force that included in the drag force. And then the battery of the voltage will decrease every time you conduct the experiment. However, I think the reporter gave me a quite good answer that maybe in his experiment that the voltage is stable. And then I want to ask the reporter if there will be a terminal velocity in his experiment. Okay, so let's go to the questions for the report.
Okay, now we move on to the discussion.
Okay, so did you check the temperature of the magnets after every time you did the experiment, since I think the temperature of the magnets will influence the intensity of the magnetic field, maybe? Yeah.
Yes, after the train runs through coil, it will increase.
Okay, so did you control this in your experiment so that your experiment won't have a big error?
What I control is that before I put the train inside the coil, the temperature should be the same as the room temperature, and the voltage should be 1.47 voltage.
Okay, so I mean, did you control the temperature of the magnets? Or the temperature of the magnets increase every time you did the experiment?
No, the part that will increase the temperature will increase is the battery.
Okay, so you mean that the battery. Okay, so the next question. So can you explain again why the train will move in the copper coil?
I will just explain in a more simple way.
Yeah,
is that okay? Please go to page 47. So here is a simple theory about why the train will move. So here, when the magnet contact the coil, it will form electric current, which if we look at this current as a electric magnet, it will look like this. So if our magnets are in this is an S pole and here is a N pole, then the front magnet will be pushed by this electromagnet, and the back magnet will be pulled by this electromagnet. So this is a simple explanation why this train will move.
Okay, so however, I have some of my opinions about this one. So do you think the magnetic field is all the same in this copper coil?
Of course, the copper coil's magnetic field will not be the same, and because as the train runs through different part of the coil will be electrified, so the magnetic field that the coil generates will not be the same.
Okay, so can you draw a picture on the whiteboard like how you arrange the magnets, like the north pole and the south poles?
Oh,
how do you arrange it?
So by this we can know that if the electromagnet, if this is the coil, and if the current is going in this direction as on my PowerPoint, then the electromagnet that the coil form will be in this, will be like this, S and N form. So the magnet that my train have should be like this, which have S and N, and the other one should be in the opposite direction, which is S and N.
Excuse me, can you try to show the board to all the audience so we can see?
Okay, so you think that the force that push the magnetic train is because the magnet will like want to move in the copper coil? Yeah.
Want to move in the...
So let's take an example. So if a copper coil is like that, and we just put a magnet inside, will it move?
Of course not.
But why will the train move in this situation?
Because there is a battery, and as I will draw it like, just say that they have already contact.
Okay.
So
it
will form an electric circuit, which you can see the magnet itself can carry current. So you will see like the current will go through here and go through the whole coil and go back to the battery and form an electric circuit.
So now I input them.
That will not affect anything, because as you can see, here is the magnetic field of these two magnets, which is Sn, Sn. And if I draw the line, it will be look like this. Here, 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 here.
Okay.
And as you can see, the direction, the vertical direction, is the one that pushes the train. So here is up, here is down. So what we need to do is that we only electrify the part between these two magnets. Or else, if you electrify the whole coil, these two parts will be
okay, I get your point. I get it. So let's say like that. So did you know if the magnetic field is stronger in the middle of the coil or on the side of the coil? Can you explain for me that when the train is moving in it?
You mean when a coil is electrified, which part of the magnetic field is bigger?
Yeah.
You mean in my experience or what? Because if we want to talk about a coil, and we know that which part of the magnetic field are you talking about?
Okay, so maybe I'll change it in another way. So first we're going to discuss another diagram first, then we'll go to this one. Okay, so like this one. So the magnetic train is like that.
Yes.
And the train, let's assume that you place it like that.
Yes.
And so when the train runs in the copper coil, it will have a magnetic field, yeah. Maybe in a direction.
You mean the magnetic field that the magnet have or the coil generated?
The coil generated.
Yeah, the coil will generate.
So do you think in this condition the train will move?
In the condition that the train has electrified the coil, yes, the train will move.
So you mean that in this case the train will move?
In this case, the train will move, yes. That is in the coil, and it has electrified the coil between those two magnets.
Okay, so however, if the like a magnetic field like that, then the force will be, the total force will be 0 on each magnet. So why will the train move?
I mean, if you input the current in the whole coil, not only the part between the magnets, the train will not get a force, because the direction of the magnetic field that generated by the magnets are in opposite direction in these two parts.
Okay.
So we can only take one part, so the force will not against itself.
Okay, so how about this one? I think that maybe, so do you think at this point, so can you draw a diagram for me, like as this one is 0, and from it, this is the position of the, okay, and this is the magnetic field's intensity. So can you draw me like a trend line, how the magnetic field will change in the copper coil?
In the copper coil.
Yeah, in each position.
In each position.
Yeah.
So if I said this is the here, so here is the start of my train, and here is the battery, and that here is the, I will say it's X. And you want me to disable magnetic field?
Yeah.
In which direction, or just the value?
Just the value, yeah.
Okay, so since here is electrified and here are the magnets, so let's first talk about the magnetic field. So if I said it's in this direction and in this direction, and here's the positive pole, so let's say the coil will generate a magnetic field that are like this. So you can see it's really complicated.
Okay.
Calculate to get the result. We cannot just draw it, or I will just say we'll have a magnetic field on it, but how it change, I'm really not sure before I actually calculate it.
Okay, so this is an interesting question, and maybe we'll discuss it in the future. So let's move on to the next question. So did you observe the terminal velocity in your experiment results?
No, because I believe that is my coil isn't long enough to reach the terminal velocity.
So you believe that it will reach a terminal velocity in the long run, yeah?
Yes, I believe, yes.
So what is the force that make the terminal velocity appear?
Well, if we would like to talk about energy first or the force first.
So you just show me the force.
Force, because if we want to talk about the force, it's really hard to find, because in our straight line, there's no force that will make it to get a terminal velocity, but I would like to talk about energy, okay?
Energy.
Okay,
so
yeah.
I want to first focus on the force.
Okay, force.
Okay.
So
you mentioned in your report
maybe
that
the air friction, okay.
You mean the air friction?
Maybe, I'm not sure.
The air drag. So do you mean that the air drag is big enough to make?
I'm not sure, because I didn't observe it in my experiment. If you want me to say a force that might against it, I will say.
Okay, so I have think of one point is that if we want to go to a terminal velocity, the drag force must be in proportional or go bigger as the velocity of the train goes bigger. It must go bigger and bigger as the train's velocity goes bigger and bigger, so that there will be a terminal velocity. So what do you think
the battery just run out of its power, so it slow down.
Okay, so what do you think about you have mentioned that the train will bounce on the.
No, I did not mention that.
Like tilt into the
Nope, I did not mention that. What I say is that the voltage that I see is that sometimes it will have a voltage on the coil, but sometimes not, and sometimes have, sometimes not. That does not mean the train is bouncing. It just means that the coil doesn't get electrified.
Okay, so in this report you cannot really explain why there's a force that causes the terminal velocity.
I did not say a terminal velocity in my report. Why do you say that I should?
Because you believe that there will be a terminal velocity, so I'm going to invest.
And how about you? What do you think will cause the terminal velocity?
Okay, so I think that is because let's say if the copper coil is like that. Okay, so when a copper coil is like that, the train, because the copper coil you cannot make it really perfect. So maybe when the train moving and we know that the kinetic friction is all the same. So there maybe when the train is moving faster and faster, and then it will dump into that one. So maybe if the velocity becomes bigger, and then this force will increase.
Can you prove it?
Yeah. But I do it in my experiment, but I can't talk about it in my.
Let's see about my experiment. Go to page 80. So here is how run it through a very long coil, but it's not made of copper because.
Sorry, the time is up, so I have to stop you. And opponent, you have 1 minute to summarize the discussion. Yeah, please.
Okay, so in our discussion, we first talk about some of the experiments methods that he might met in his experiments, and I think he gave us really good answers. And then we talk about why the train will move. And I think the report, and I think we cannot get into cannot reach a consensus that why the train will move, because I think the magnetic field in the copper coil is not the differences between the magnetic field in the copper coil is the main cause that makes the trains to move. So, and then we talk about terminal velocity. However, the reporter did not show the terminal velocity in his report. However, he told me that he believed that there will be a terminal velocity. So, but he can't prove that what force caused the terminal velocity. And he also asked me about how force is it, but I think that is involved my experience, so I can talk about it. And maybe the reporter can improve it in the future. And thanks for your listening.
Okay, thank you. Opponent, please get on the stage.
I have some
ready to
questions
answer
for
questions.
the reviewer. So you think that only friction will have effect of the dragging of the battery?
Dragging of the battery.
Yeah, because the acceleration will lowers, right?
Maybe, but I'm not sure because I did not observe that.
So you assume right now that it is friction?
Maybe the air friction will make the force against it become bigger.
Okay, thank you. So is there a terminal velocity?
No, I did not observe that. I believe there will be a terminal velocity.
You didn't observe, but you believe there will exist a terminal velocity.
Yeah,
okay, thank you. So do you consider the resistance between the contact of coil and magnet?
Resistance between them, of course.
In your system, the resistance of the magnet.
You mean the contact resistance or the resistance of the coil wire?
The resistance between of the contact.
The contact resistance I cannot measure it, but I believe the resistance that the coil makes will be very small because it is the wire.
Okay. In your report, the voltage disappears sometimes, right?
Yes.
And why?
Because I believe that in some points the train will not electrify the coil because it might be not
because sometimes it
might not completely contact the coil when it runs through it.
So in your opinion that because it won't be attached with the coil, so the voltage disappears?
Yes.
Okay. So that will be my questions. Thank you.
Okay, we move on to the preparation of the reviewer. So, reviewer, please take the floor. You have 4 minutes.
Okay, good morning everyone. This will be my review of the magnetic train. So first, this is the introduction as we are all familiar with. And let's go to the, rewind of the reporter's report. So first from the theory that
the reporter claims that magnetic field will provide the force to move the magnetic train, and also there will be the torque, which happens on the horizontal and vertical directions. And in their experiment, they discuss about the preliminary measurements, which is the magnetic field, and only the Fx matters. Well, and the velocity will be related with the torque direction, and the voltage, when it's still, it is stable, and when it's running, it's not stable. And also, of course, the other parameters. And for the conclusion that the acceleration will be due to the magnetic field, and the current push the train, and so some of the parameters well matters. Now let's look at the clash between the opponent and reporter. So they consider the distribution of magnetic field. The opponent asks, when the magnetic field is uniform, will the train still move? But the reporter answers that they are not sure of the distribution of their system. And in our perspective, we don't think so. If the magnetic field is uniform, the train will still move. And for the second clash, it's about the terminal velocity. And the opponent asks, according to your report, you believe there is a terminal velocity. And reporters said that the coil isn't long enough, so they didn't observe it. But if the coil is long enough, they might be able to see the terminal velocity. And the opponent thinks that the cause may be friction, and the reporters mentioned about the drag. And in our perspective, we think there is a terminal velocity according to the Lenz's law, because when the current in the system change, according to the Lenz's law, there will be a induced magnetic field that will resist the motion. So we don't think it's because the air friction or some kind of drag force. So for the missed point, they didn't consider about the induced magnetic field. However, we all know that the current will change during this system. So we believe this will be an influencing effect. But however, both the opponent and the reporter didn't give consideration to it. So we believe this is the missed points. And these will be our review.
Okay, thank you. Yeah. So now is a concluding remark of the reporter.
So for a concluding remark, how I measure battery is all the same. Is I measure its voltage before I use it. And about the terminal speed, what I say is that there might be a force that against them to lead into a terminal speed, but it will definitely not be kinetic friction, which will be a constant. No matter what change the speed or whatever, it will always be a constant. If we are talking about the terminal speed, it will not be the standard, it will not be the friction that gives it the terminal speed. And why I believe there will be a terminal speed is that I look at the part about the energy. So if we look at the battery, the power that the battery can produce is limited. It cannot give a power which is very big, so it will be a limited power. So when the train is moving in the coil, it will get a force and it will have a velocity. So by this, we can know that the power that it gets kinetic energy will be F times velocity. So as the velocity becomes bigger, the power the train gets kinetic energy will also become bigger. But I believe that the energy in this system are provided by the battery, which the power is limited. So the power that the train gets kinetic energy can cross this line, which is bigger than the maximum power that the battery can produce. So that's why I think there is a terminal velocity. But I cannot explain what kind of force might cause this, because I did not observe it. But this is the explanation about why I think there is a terminal velocity. Thank you.
Okay, thanks for all three teams. All three presenters, please get on the stage and get ready to answer questions. So, are there any questions from the jury? Yeah, please.
For the reporter, in your calculation, your acceleration is too small. So your explanation is the battery is not charging the coil all the time. So please tell me, if the battery is not charging the coil, what the motion will be?
I believe that by the first law of Newton's law of motion, it will still be moving in the same speed, but it will still get a friction.
So you're only charging 1/3 of the time, so that means you should be able to observe from your trajectory.
No, I cannot, because if you look at the chart again, you can see that the period is really small, really small. And can you go to the chart? Where's the chart is not this chart. Which one? Huh? I mean the voltage measuring. The one I was measuring the voltage. Page 32. Yeah, as you can see, the unit is millisecond, and here it's really short. We cannot observe it by any high-speed camera.
Okay. So are there any other questions? Yeah, please.
Okay, I think I'm going to extend the discussion a little bit more. So the question really asks the problem says the train's speed and power. So you would think for the magnetic train, I mean the power is from the battery.
Yes.
So it's assumed with fixed power, how are you going to improve the speed? That's maybe the major issue.
Oh, to improve the speed.
Yes, I mean just like a transportation, you want to put a fixed amount of power, but then you can gain the speed. So based on that, what you have any comment on that, or you can modify your device to get higher speed but with fixed power?
I believe that as the speed of the train becomes bigger, the power that it gets, kinetic energy will become bigger. So I believe that it's really hard to just discuss about the power and the speed.
So your answer is with fixed the power, then the speed must be proportional to the power, right?
Not really. I believe that there are more to consider. Like.
Okay, that's okay. Maybe let's switch to the opponent. What do you think? My question. With the fixed power, how are you going to gain the speed?
You mean fix the power?
Yeah, the power. That's the purpose for transportation, right?
Okay, so I think that depend on relevant parameters, and I think the lower resistance and maybe it will cause the train to move faster.
I give you a hint. You said about the terminal speed.
Yeah.
Yeah. Terminal speed because of what? Then how are you going to do something so you can gain speed on that?
So you want me to talk about the terminal? Just
how to increase the terminal speed in your case?
Or maybe we can like making the diameter of the coil smaller, or maybe like the turns density bigger. And you said that we have to fix the power, so maybe we will just use the same battery, and we'll change the shape, the condition of the coil to change the terminal velocity.
Well, then move to the reviewer. The same question: if we tilt it, I mean, there may be vertical force. So if the battery is slightly tilted upwards, you would think that would gain speed or not?
You mean, well,
it will be vertical.
There will be vertical torque, and will it help the speed?
Right.
Okay. Well, I don't think so, because there are gaps between the coil, and the torque is actually like bouncing, which makes it more, I think what makes it slower.
How about if the top touch the coil too? Or the, back to the reporter,
No.
just shortly.
No, shortly.
Sorry, if the torque will not make the train have this big movement.
One side touch the bottom, the other side touch the top.
That's not going to happen, because if you get a torque, what you do is that you accelerate the rotating, but the time as soon as you leave the coil, the torque will disappear. So you're never going to reach the top of the coil.
Are there any other questions? Yeah, please.
I think the reporter gave a final conclusion of the terminal velocities, and both of you have chance to challenge this model. I think. Could you comment on this model of terminal velocity, please, from a reviewer?
I believe it could reach the terminal velocity of this model. However, the reporter thinks it is only because that the length of the coil isn't long enough.
Your comments. What's your comments for this model?
My suggestion for the reporter.
During the discussion, so I give you a chance to feedback the problem here.
To talk about the problem. Okay, so I think this model, if we can consider about the effect of the Lenz's law, it could make it better to explain.
How about the opponent? How do you think his answer of the terminal?
The reason for the terminal velocity. Okay, so I think the main cause of the terminal velocity is when the magnetic train passes by, and I think the current is not stable on the copper coil. Yeah. Since there are some reasons that if there are drag force acting on the magnetic train, but however the drag force not only including the friction, there are other, like the train will tilt, and if the velocity of the train increases, the drag force that caused by the train tilts, I think it will influence more. So I think, yeah, that's why the terminal velocity will appear.
Okay, if there are no more questions, we move on to the grading. So. Okay, now the score for the reporter, please. 9, 8, 9, 9, 8, 8, 8, 7, 6, 8, 9. For the score for the opponent are 8, 8, 9, 8, 7, 6, 6, 7, 5, 7, 9. And the score for the reviewer are 8, 9, 9, 7, 6, 7, 7, 8, 6, 7, 8. Thank you. And any comments from the jury for the grades given? Yeah.
Some comment for the reporter. According to your data, your train motion is not constant acceleration. So that's when you have to find a way to explain why it's not constant acceleration. And your model of determinant velocity is not pretty correct, because even though you have power limited, as long as you don't have resist, the force getting smaller but still moving accelerating. So that's when you won't reach any kind of terminal velocity. If you need to reach a terminal velocity, you need to have something that is velocity dependent resist. So that's when you can balance your force in certain ways, so you reach the terminal velocity. That's something you should think about it.
Any other comments? So if there are no more comments, I would thank all three teams for a very exciting tournament and the discussions, and thanks all the three teams. Yeah, thank you. Meanwhile, I would like to at the end of the last stage, I would like to give a word to deliver two awards. One is the 最佳科技创意奖。那这个奖，sorry， 我 switch 为中文哈，我还是比较喜欢讲中文。这个奖我们的选择方式是，就是在做实验的时候比较多的这个data 是用这个digital 的方式去 access。那我们经过评审团决定之后，我们这个奖是颁给彰化女中的谢构普朗克。那我们请小思达小院长来颁这个奖。可不可以请全队的人都上来？接下来我们要颁的是这个骑士精神奖。那这个奖基本上颁发的原因是因为其实在竞赛的过程中，我们有一两队的这个同学遭遇到了很大的挫折，而且他们克服了这个困难。那完成了这整个竞赛的过程，所以我们觉得他们的精神非常值得这个表扬一下，所以我们就颁发了这两个奖。那这两个奖有两个队伍，那第一个队伍是那个 Team Plasma 维格高中的，这是3位同学，因为这3位同学他们，对 Team Plasma， 有这上头画了太多东西。那他们的情况是在昨天早上的时候，他们的队员忽然都不见了。那他们最后最后决定留下来，在这个继续奋斗。那这3位同学是林义涵、林晨宇和台静，有在现场吗？OK， 那 其实他们昨天有跟我讲为什么今天会没有来，因为他们要期中考，所以这我觉得是这个也是为什么我会想办这个奖，因为他其实这2天就期中考了，那他们还非常努力的来参加完这个活动。对，那另外一个队伍呢是Fabulous Physics， 华盛顿高中，那可不可以？华盛顿高中有在吗？那可不可以请上台来接受这个奖？那我们请我们物理系系主任刘祥明老师来颁发这个奖。谢谢。那今天早上的这个竞赛就到这边结束。那我想这个主任有话跟我们讲一下。
NTNU Physics will give the concluding remarks in Chinese. OK， 第一点呢，在过去3天呢，24队所有的同学都坚持到底，我们给自己一个掌声，好不好？那第二点呢，各位同学，我们要不要谢谢这些辛苦的评审老师，给他们一个掌声？第3点呢，最辛苦的人是谁呢？每天比我们早来，比我们晚回家的，就是我们现场的工作同仁，这边的工作同仁，后面的工作同仁，我们以最烈的掌声谢谢他们。